The air sometimes hums with stories we almost believe, doesn't it? Tales of lights in places no bulb belongs, of glowing spheres drifting silently through walls, of strange electricity floating in from the dark like a thought you didn't invite. I'd like to begin with one of those: ball lightning, the ghost of the thunderstorm world. Hello there, and welcome to the Sleepish Science. Whether you've just slipped beneath a blanket or you're walking through the stillness of early afternoon, I'm so glad you're here. If you feel like sharing, I'd love to know where you're listening from and what time it is for you right now. And if by any chance you're the sort of person who thinks lightning should come with clouds and thunder, well, ball lightning would like a word, possibly through your living room wall. So before you drift into dreamland, go ahead and like and subscribe. Your future sleepy self will thank you, or at least give you a thumbs up in your dreams. Let's begin, gently. More than a few people have claimed to see it, a glowing grapefruit-sized orb floating just above the ground, or maybe waist-high, emitting no sound, sometimes hissing, sometimes pulsing, occasionally exploding. It may last a few seconds or reportedly drift about for almost a minute. It has been spotted during thunderstorms, yes, but also in perfect calm, on ships, in airplanes, in kitchens, in fields. Perhaps most strangely, these balls sometimes pass straight through closed windows without breaking the glass, behaving less like an object and more like an idea with voltage. Skeptics, especially in the early days of atmospheric science, dismissed these reports as hoaxes, hallucinations, or simple misinterpretations of regular lightning after images. Yet the sheer volume and strange consistency of eyewitness accounts began to mount, particularly from aviators during the 20th century. Pilots during the Cold War, including some flying military aircraft, described orbs that danced along their cockpits or floated inside the fuselage, leaving behind the smell of ozone or burning insulation. One particularly well-documented case came from the flight engineer of a Soviet Tupolev airliner, who during a storm over the Caucasus Mountains reported a glowing ball entering the cockpit, hovering silently, and then disappearing through the rear cabin. That report, among others, drew the attention of physicist Yuri Stakhanov, who began cataloguing dozens of similar accounts, many eerily consistent in detail. He was one of the first to suggest ball lightning might be its own kind of plasma structure, plasma being the fourth state of matter, an electrically charged soup of ions and electrons. But unlike the bolt from the blue kind of lightning that lasts for a few millionths of a second, ball lightning seems weirdly stable. That's where the mystery thickens. One line of thinking, developed more than 2 decades ago by Brazilian researcher Antonio Pavão and his colleague Gerson Paiva, proposed that silicon vapor may play a role. They speculated that when regular lightning strikes sandy soil, it could vaporize some of the silicon-containing compounds and trigger a chemical reaction that forms a glowing, self-contained structure. In the lab, they even managed to create small, bright orbs lasting several seconds, though these were fleeting and not free-floating in air. Another idea, championed by the late German physicist Ulrich Amerlan, involved microwave radiation. He proposed that a bolt of lightning might produce an intense burst of microwaves which, bouncing inside a spherical cavity of ionized air, could trap energy long enough to glow visibly. This theory gained some traction when Chinese researchers at Northwest Normal University filmed what they believed to be ball lightning during a thunderstorm in the Tian Shan Mountains. The orb appeared during a lightning strike and exhibited a spectrum similar to burning soil, suggesting the silicon hypothesis again, but it could also align with the microwave model. Of course, no one theory explains all the weird behavior. The passing through glass trick remains especially puzzling. Some have half-joked that the phenomenon behaves more like a quantum entity than a weather pattern, appearing where it shouldn't, ignoring physical boundaries, and leaving physicists rubbing their temples like overstressed wizards. Yet, it's not all speculation. In 2014, physicist Mike Dunning, working out of a small lab in New Mexico, used a cleverly timed burst of microwave energy inside a vacuum chamber and accidentally produced a floating glowing sphere. He wasn't even trying to recreate ball lightning, he was just testing microwave pulses for propulsion experiments. This unintentional spark revived interest in controlled experiments, and similar trials since have created phenomena that are ball lightning, adjacent if not identical. Still, none of these recreations fully match the wandering, mischievous fireballs people swear they've seen drifting across meadows or slipping into barns. Could it be that we're chasing more than one phenomenon? That ball lightning is an umbrella for different effects, some plasma, some chemical, some electrostatic, and some, dare I say, psychological. Certainly, the human brain is good at pattern filling. Our visual cortex delights in interpreting bright lights and phantom shapes, especially in storms. But even allowing for the quirks of perception, some of these events come with measurable electromagnetic surges. Portable field sensors have occasionally picked up sharp electric field pulses when ball lightning is observed, suggesting this isn't just in the viewer's mind. It leaves us with a delicate balance, open skepticism, tempered curiosity, just enough doubt to keep the explanations honest, just enough wonder to keep looking skyward, or maybe toward the toaster, if you're feeling brave. Because if these glowing spheres are real, and the mounting evidence suggests they represent a kind of naturally occurring energy structure we barely understand. Not quite fire, not quite plasma, not quite illusion, something drifting at the edge of what we can describe, and if they float just outside the reach of our instruments, well, perhaps that's not where science ends, perhaps that's just where it gets interesting. And while glowing spheres may drift through quiet living rooms or pilot cabins, some lights emerge from the ground itself, uninvited and unsettling. Let's stay with these mysteries of light, but now shift our gaze down to where the Earth holds its own static secrets. Because sometimes, just before the ground moves, the sky begins to glow. They're called earthquake lights, rare, luminous events, reportedly seen in the moments, hours, or even days before a major seismic upheaval. The accounts are startlingly vivid, flashes like sheet lightning, where no storm exists, bluish columns rising from the hills, glowing clouds hovering over fault lines, and even flame-like tongues licking at the horizon. These aren't tales from folklore alone, they're part of the geological record now. In January of the early 21st century, just before a major earthquake struck southern Peru, dozens of people witnessed blue and white lights rippling above the Andes. A decade earlier in China's Sichuan province, security cameras caught odd flashes illuminating dark skies, moments before a devastating tremor. One video, often shown at conferences on geophysical anomalies, shows the parking lot of a residential complex lighting up like a flickering neon sign just before the shaking begins. And these are far from isolated cases. In 2014, physicist Friedemann Freund, a senior scientist at the NASA Ames Research Center, published a theory that might explain them. He proposed that immense mechanical stress within rock, particularly types rich in quartz or other crystalline structures, can activate dormant electrical charges. In essence, when tectonic plates grind and flex under pressure, they may release charged particles that migrate to the surface, ionizing the air and creating light. This idea builds upon the piezoelectric effect, discovered in the 19th century by the Curie brothers. In a piezoelectric material such as quartz, applying mechanical stress can generate an electric field. Squeeze it hard enough, say under the pressure of 2 continent-sized slabs of earth, and it might create a powerful electrostatic discharge. Freund's work took this further. He suggested that in stressed rock, tiny defects allow pairs of oxygen atoms to break apart, forming positively charged holes in the mineral lattice. These holes can flow like current, building up enormous electric potentials over wide regions of crust. When they reach the surface, they may ionize the atmosphere, triggering brief, localized displays of light. This isn't just a clever model. Laboratory experiments have shown that when granite is crushed under pressure, it emits electromagnetic pulses and even visible glows under certain conditions. In the Seismic Electric Signals Lab in Greece, researchers have used such findings to develop devices that attempt to detect these pre-seismic electric fields, claiming predictive success in some regional earthquakes. But this is not yet settled science. The geophysics community remains politely split. Some researchers welcome the data, but caution that not all quake lights come from tectonic stress. In Italy, for example, a group studying the L'Aquila earthquake proposed that shifting ground released radon gas, which ionized the air in a way that could produce brief flashes. Elsewhere, atmospheric physicist David Sentman pointed out that in some areas, earthquake lights may actually be misunderstood, sprites or transient luminous events caused by upper atmosphere disturbances, not seismic ones. So we may be looking at multiple mechanisms here, a blend of subterranean friction, gas emissions, and perhaps even atmospheric echoes of the quake itself. And then, there's the matter of folklore. Long before the Richter scale, Indigenous groups across the Americas described sky serpents or earth stars appearing in times of upheaval. In Japan, glowing orbs were seen hovering over hills before large quakes, recorded by samurai scribes as signs of the gods' displeasure. The Navajo people speak of ground fire dancing at the edge of vision in the moments before the world rumbles. These traditions, handed down in song and symbol, weren't weather reports. They were warnings, visceral, remembered, and sometimes repeated. Of course, we must tread carefully here. Anecdotal evidence is notoriously tricky, and confirmation bias loves a dramatic glow. One person sees a flash during a stressful night, and a tremor the next morning makes it unforgettable. But when multiple cameras, instruments, and observers converge, the story gains teeth, and sometimes those teeth glint in unexpected places. In the 1976 earthquake near Tangshan, China, reports describe the entire skyline briefly glowing violet. This occurred before dawn, hours before the quake hit. Emergency workers later told journalists that the glow seemed to pulse from the ground up rather than from the clouds down. Why would earthbound light reach toward the heavens? That's where the idea of ionospheric coupling comes in. Some researchers, including Kosuke Hattori at Chiba University, have found disturbances in the Earth's upper atmosphere just before major quakes. These disruptions affect radio waves, satellite signals, and even local magnetic fields. One idea is that electrical energy from the lithosphere, the rocky crust, travels upward, disturbing the atmosphere as it rises. If true, it means our planet might send up warning flares of its own making, like an old friend grumbling before it gets up from a chair. Still, earthquake lights remain enigmatic. No one's yet built a definitive prediction system based on them. But they do remind us that Earth is far from passive, that its deepest tensions can surface not only in tremors but in subtle, fleeting flares of light, warnings written in static, the kind you don't notice until someone says, "Did you see that?" And then the ground begins to move. And if the ground can crackle with tension and light, then imagine what a mountain can do when it throws its entire insides into the sky. Let's climb now, not just in elevation but into eruption, because sometimes the Earth doesn't just whisper with static. Sometimes it roars, and the sky answers with thunder it creates itself. Volcanic lightning is the sort of phenomenon that makes even seasoned geophysicists do a double take. Picture this, a plume of ash billowing miles into the atmosphere, dense and grey and full of teeth. And then just when you think nature has made its grandest statement, flashes of lightning streak across the column, igniting the darkness like divine punctuation. It's not just beautiful, it's electric in every sense. For centuries, these flashes were thought to be legends, the fire-laced temper tantrums of angry mountain gods. But the truth turns out to be far more charged and far more fascinating. Volcanic lightning, also called a dirty thunderstorm, doesn't always need rain clouds or external weather patterns. It generates its own tempest from the churning friction within an eruption column. Here's how it works, as best as current science can tell. When a volcano erupts, it hurls out a turbulent mixture of gas, ash, rock fragments, and superheated vapor. As these particles collide at high speeds, they build up static electricity, like rubbing a balloon on a wool sweater, except the balloon is a boulder and the sweater is made of boiling gas. The collisions cause particles to become electrically polarized, meaning some carry a positive charge, others a negative one. And as these separated charges accumulate, the electrical field grows stronger until finally, zap, discharge. A bolt of lightning erupts within the plume, leaping from one part of the cloud to another. Sometimes it arcs out of the column altogether, striking the surrounding terrain or splitting the air with thunderous cracks. The sound is often lost in the cacophony of the eruption itself, but the light is unmistakable. Take, for example, the eruption of Mount Sakurajima in southern Japan. This stratovolcano, known for its frequent and photogenic outbursts, has provided researchers with an ideal natural laboratory. High-speed cameras installed around the volcano have captured thousands of lightning events within ash plumes, sometimes occurring just seconds after the initial blast. During a particularly active period in the early 21st century, researchers from the University of Tokyo documented more than 100 lightning discharges in a single eruption lasting less than 5 minutes. Closer to home, the 2009 eruption of Mount Redoubt in Alaska produced a similar spectacle. Photographs from the event show spiderweb-like arcs of lightning spreading through the ash column, casting eerie blue-white shadows across the landscape. These images aren't just visually stunning, they also help volcanologists study the timing, strength, and dynamics of eruptions from a safe distance. And then there's Mount Eyjafjallajökull in Iceland, the volcano that grounded half of Europe's air travel for weeks. During its infamous 2010 eruption, it released so much fine ash that commercial pilots were told to steer clear for fear of engine damage. But even more captivating than the disruption was the lightning pulses of light recorded by satellite and observed from the ground, streaking through clouds like battle flares in a silent war. Interestingly, the amount and frequency of volcanic lightning often correlate with the size and density of the ash cloud. The finer the ash, the more surface area is available for charge buildup. This means that the most explosive eruptions, the ones that inject material high into the stratosphere, are often the most electrically active. In fact, the presence of lightning has become an important tool in eruption monitoring. The United States Geological Survey, in collaboration with the Alaska Volcano Observatory, now uses specialized sensors known as lightning mapping arrays to detect and triangulate volcanic lightning. These systems work much like weather radar, but are tuned to radio frequencies generated by electrical discharges. When volcanic lightning is detected, it can serve as an early warning, indicating that an eruption is underway, often before ash or gas reaches the surface. But volcanic lightning doesn't just illuminate the sky, it leaves a mark. In 2016, volcanologist Corrado Cimarelli and his team at Ludwig Maximilian University in Munich conducted field experiments to study how ash particles become charged. They built a small-scale volcano simulator, blasting compressed air mixed with volcanic ash through a steel pipe into a controlled chamber. What they found was that not only does ash become charged on collision, it can also transfer that charge to other particles, setting off a chain reaction of electrification. These findings help explain why some plumes sustain lightning for long periods, even after the initial explosion. So what's really going on here? Some scientists believe that volcanic lightning and regular thunderstorm lightning are two sides of the same coin, driven by charge separation and field breakdown, but differing in scale, speed, and materials. While thunderclouds rely on the collision of ice crystals, volcanic plumes use ash and rock as their electrical conductors. Others suggest the phenomena may diverge more sharply. For instance, lightning researcher Carlos Lope from the National University of Colombia has proposed that the ash cloud's composition, including minerals like feldspar and magnetite, may influence the type and behavior of the discharge. Certain eruptions, he notes, produce more branched, chaotic bolts than others, suggesting a chemical fingerprint unique to each volcanic event. And let's not forget the sheer drama of it all. Lightning leaping from a mountain's mouth isn't just science, it's poetry on a planetary scale. It reminds us that the Earth is still a dynamic, breathing, belching, sparking world, that even in its most violent moments, it produces beauty, sometimes in the flash of an arc through falling ash. There's something curiously satisfying about a mountain that not only spews molten rock but also decorates its tantrum with electricity, like a dragon with a flair for the theatrical, or a thundercloud with stage presence. And just when we think we've understood how storms behave, nature writes a new script, this one in magma and voltage, with lightning for punctuation marks. Because the sky does not always wait for clouds to find its fire. If volcanic lightning is thunder dragged from the Earth's throat, then what comes next is its celestial whisper, brief, radiant, and reaching from the clouds to the edge of space. We've watched lightning dart across skies and erupt from mountains, but now we turn our gaze upward, far above even the highest clouds, into the realm where air thins into space. And flashes are not just violent but almost shy. Meet sprites, blue jets and elves, ethereal cousins of lightning, rarely seen, often misunderstood, and until fairly recently dismissed as folklore or optical illusion. It began with pilots, as so many strange sky stories do. Flying above storm clouds in the latter half of the 20th century, commercial and military aviators would occasionally report flashes not within the storm, but above it, ruddy glows or quick flickers darting upward toward the stars. These reports were largely ignored by meteorologists, chalked up to the tricks of night vision or the fatigue of long-haul flying. After all, everyone knew lightning went down, or at least sideways, but never up. Except it does. The proof came in the form of a grainy video captured by accident. In the late 1980s, scientists at the University of Minnesota were testing low-light cameras pointed toward thunderstorms in the Midwest. Reviewing their footage frame by frame, They spotted something bizarre, a reddish, tendrilled flash extending from the top of a cloud into the upper atmosphere. It lasted only milliseconds, but it was enough. They had caught a sprite. Sprites are upper atmosphere electrical discharges that occur high above thunderstorms, sometimes as high as 60 miles above the Earth. They're usually reddish-orange in color, shaped like jellyfish, carrots, or even feathered trees. And they don't behave like ordinary lightning. Instead of branching horizontally or grounding toward Earth, sprites leap upward in massive complex formations that can stretch for tens of miles in height. Why? Well, lightning is more democratic than we tend to think. When a powerful bolt of cloud-to-ground lightning discharges below, it creates a sudden imbalance in the upper atmosphere. The energy released by that bolt reverberates upward, triggering a secondary discharge, a sprite, as the atmosphere tries to stabilize itself. It's like the clap of thunder that echoes not only across the sky, but up through the ceiling of our breathable world. In fact, one study from Stanford University led by Umran Inan revealed that a single cloud-to-ground lightning strike can release enough electromagnetic energy to trigger a sprite dozens of miles above the storm, even when there's no visible activity at the surface. Using radio wave detectors and satellite imaging, Inan's team mapped sprite activity in synchronization with lightning strikes below, confirming that these high-altitude flashes aren't random, they're ripple effects. Then there are the blue jets. Unlike sprites, which appear above storms, blue jets shoot from the top of a thundercloud, piercing upward in narrow conical beams. They're fast, bright, and surprise, blue. Their coloration comes from the ionization of nitrogen in the stratosphere, which glows blue when electrically excited. Blue jets were first captured by the crew of the space shuttle in the early 1990s, a discovery that sent meteorologists scrambling to understand how thunderclouds could produce electrical discharges upward into the mesosphere. Recent data gathered by the European Space Agency's Atmosphere Space Interactions Monitor, mounted on the International Space Station, has offered breathtaking footage of blue jets, some extending over 30 miles in less than a second. The high-speed cameras also revealed blue bangs, ultra-fast bursts of blue light that may represent the beginning of a jet event, although their exact mechanics are still being pieced together. And then there are ELVs. Yes, ELVs. Technically, this acronym stands for Emission of Light and Very Low Frequency Perturbations due to electromagnetic pulse sources. But let's be honest, ELVs is more fun. ELVs are vast, disc-shaped glows that appear in the ionosphere, roughly 60 to 65 miles above Earth, expanding outward at the speed of light in response to powerful lightning strikes. They look like glowing halos, briefly illuminating enormous areas of sky before vanishing within milliseconds. Captured only by satellites or ultra-sensitive cameras, they're almost impossible to see with the naked eye. They're the shyest of these sky spirits, an electromagnetic sigh from the planet's skin to its halo. And yet, despite their brevity, ELVs may play a surprisingly important role in atmospheric chemistry. Research from Kyoto University suggests that these flashes could influence the behavior of upper atmosphere molecules, including nitrogen oxides and ozone. Each flash may only last 1,000th of a second, but over time their effects could add up, subtly shaping the electrical balance between our planet and space. Sprites, jets, ELVs, they all belong to a family called transient luminous events. The term was coined in the 1990s. Once it became clear these flashes were not the optical equivalent of Bigfoot, but a regular, albeit elusive, part of thunderstorm dynamics. And while the general public still rarely sees them, scientists now chase them actively, especially from space. Balloon-borne instruments, high-altitude aircraft like NASA's WB-57, and ground-based observatories in Peru, Texas, and the Australian outback all work together to map these brief fireworks of the upper sky. With each sighting we learn more, not just about lightning, but about the complex relationships between Earth's weather and the space environment above it. What's remarkable is how these lights behave not like bolts, but like gestures. Sprites curl upward like tendrils of flame. Jets pierce through like the sharp exhale of a breath. ELVs stretch outward, rippling like a stone splash across a still pond. They're not just electrical events, they're stories written in a language of plasma and pulse. And like all good stories, they leave a trace, subtle, brilliant, and reaching toward whatever lies beyond the sky's edge. Because when the clouds run out of room to speak, the silence above them answers in light. And sometimes the sky's answer is not a flash but a glow, a soft blue halo dancing along the rigging of a ship or the steeple of a chapel, silent and almost serene. Let's turn now from high-speed bursts to something quieter, something ancient. If sprites are the fireworks of the upper atmosphere, then St. Elmo's fire is its candlelight. This phenomenon, named after the patron saint of sailors, has guided nervous crews through stormy seas for centuries. Imagine standing on the deck of a wooden ship, wind howling through the sails, waves like hills rising in darkness, and then suddenly the masthead begins to glow with an electric blue fire. It crackles faintly, curling like liquid flame around metal points and ropes, a sign they once believed of divine protection. But it is not fire. Not really. St. Elmo's fire is a form of plasma, an ionized glow that appears when the electric field in the atmosphere becomes strong enough to ionize air molecules, but not strong enough to spark lightning. The glow clings to sharp or pointed objects, weather vanes, fence posts, airplane wings, even the horns of cattle. It's nature's way of softly exhaling static tension. The underlying mechanism is known as a corona discharge. When the electric field near a pointed conductor, say the tip of a mast, exceeds a critical threshold, it causes the air around it to become conductive. Electrons are stripped from their atoms, and the gas glows. The color depends on the gas involved, but in Earth's atmosphere it tends to be blue or violet because of nitrogen's ionization characteristics. This isn't some quaint maritime myth. St. Elmo's fire has been documented in modern times across many settings. In fact, pilots often report it as a faint violet glow along cockpit windows or engine intakes during turbulent or electrically active flights. During World War II, bomber crews flying through thunderstorms described halos crawling along their wings. The phenomenon became so familiar to some flight crews that they considered it an omen either of safety or of trouble ahead, depending on who you asked and how much coffee they'd had. One of the most dramatic cases occurred during the 1960s, when a research balloon launched by the National Center for Atmospheric Research was struck by St. Elmo's fire while passing through a thunderstorm at high altitude. The sensors recorded a continuous corona discharge that lasted nearly 3 minutes, providing some of the first detailed measurements of the electrical environment around this glow. And yet, even today, there's confusion between St. Elmo's fire and ball lightning. Both involve glow, both sometimes appear in storms, and both occasionally drift through strange places. But they are distinct. St. Elmo's fire does not float, it clings. It doesn't explode, it shimmers, and it doesn't require exotic explanations. Just a strong electric field, some conductive geometry, and the will of the atmosphere. In technical terms, the threshold for a corona discharge in air is about 30 kilovolts per centimeter for a sharp point, but far lower for a curved or blunt object. This makes metal spikes, masts, antennas, lightning rods ideal candidates. Once the field surpasses this point, it strips electrons from nitrogen and oxygen molecules, producing the characteristic glow. And unlike full lightning, which neutralizes the charge with a sudden jolt, St. Elmo's fire is a slow leak, a kind of luminous pressure valve for the storm's tension. Interestingly, the glow can even produce faint sounds. Listeners sometimes describe a buzzing or crackling noise, like bacon on a griddle, or the whisper of static over a radio. This is due to tiny rapid discharges within the ionized air, which vibrate nearby surfaces and create audible effects. It's lightning in a minor key, and while the glow is largely harmless, unless you're in a deeply conductive setting, it has practical importance. For example, St. Elmo's fire can interfere with radio communications, as the ionized air around antennas disrupts signal clarity. Some military aircraft are equipped with sensors to detect and compensate for corona discharge interference during operations. In rare cases, the effect can also indicate a dangerously high charge buildup, prompting caution before full lightning discharge occurs. But beyond the science, there's the wonder. Sailors of old weren't wrong to feel comforted by the glow. They saw it as a sign that they were not alone, that something watched, that something shimmered in the dark with them. Christopher Columbus noted it during his voyage to the Americas. Antonio Pigafetta, chronicler of Magellan's circumnavigation, wrote of a blue flame dancing atop the rigging as a portent of divine approval. And throughout the Mediterranean, the glow was associated with Saint Erasmus of Formia, Elmo, who, according to legend, continued to preach during a thunderstorm, his words lit by heavenly fire. The glow is mentioned in Shakespeare. seen by superstitious mariners in The Tempest, and traced through the journals of explorers and natural philosophers alike. Benjamin Franklin even sought to reproduce the effect with his pointed lightning rods, hoping to draw off electrical charge slowly, an idea partly inspired by St. Elmo's fire. In the end, this gentle blue glow offers a kind of reverse thunder, not a shout but a murmur, a way for the sky to say, "I'm full, but I won't break. Not yet." It reminds us that electricity isn't always forceful. It can be subtle. It can curl around the corners of the world in quiet arcs, flickering with the same elegance as fireflies. Even in storms, there are soft moments. And sometimes when the storm is strongest, the world shines its softest light. Of course, not all electrical mischief belongs to skies or ships. Sometimes it crawls through dust, quietly, invisibly, yet brimming with charge. Let's lower our gaze now, from the heights of masts and mountains to the dry, crackling realm of sand and wind. Because even the smallest particles swept into motion can stir up a storm of their own. I'm talking about static electricity in dust devils, sandstorms, and their wind-blown cousins. Picture a desert, not a lifeless place, but a vivid one. Heat ripples off the dunes like invisible curtains, and the ground, hot enough to bake bread, releases plumes of dry air skyward. As the day warms, spiraling columns of air may form, swirling dust into the shape of miniature tornadoes. These are dust devils, small, but often spectacular. They've been captured on film dancing across Martian plains and Arizona highways alike. Sometimes, they stretch 30 feet high. Other times, they tower taller than trees. What they all have in common is friction, and with friction comes charge. As dust particles are lifted and collide, they exchange electrons, some gaining, others losing. The process is known as triboelectric charging, a term that simply means rubbing into charge. It's the same principle behind scuffing your socks on a carpet and getting zapped by the doorknob, only scaled up to planetary dimensions. When enough charge accumulates within a dust cloud or sandstorm, the electric field can grow strong enough to cause discharges, snaps of static, faint glows, even visible sparks. And not just in theory. In the early 21st century, researchers from the Chinese Academy of Sciences conducted field experiments in the Taklamakan Desert. They installed electric field sensors near the edges of large sandstorms and found that some events generated voltages comparable to weak thunderstorms without a single drop of rain. The sensors recorded sudden spikes in charge, sometimes producing faint flashes and audible crackling. In at least 2 instances, instruments picked up low-frequency radio noise, consistent with minor electrical discharges. These aren't just idle sparks. They can affect everything from communication equipment to natural chemistry. Consider this during sandstorms in Saudi Arabia. Oil pipelines are routinely monitored for static buildup. Enough charge across a long pipe can lead to discharges strong enough to ignite flammable vapors. In one documented incident near Dhahran, a lightning-like arc jumped from a pipe to the sandy ground, igniting a minor fire caused not by lightning from above, but by a storm of sand below. Similar concerns plague Mars exploration. The red planet is a haven for dust devils and sandstorms, and its thin atmosphere and dry surface make it even more susceptible to charge accumulation. During NASA's Phoenix mission, instruments recorded unexpected voltage surges during Martian dust devils. While no visible lightning was detected, the readings suggested localized electric fields strong enough to influence sensitive electronics. This led to a cautious redesign of shielding protocols for later rovers, such as Perseverance. And let's not forget the famous Bedouin folklore, in which travelers speak of singing sands, grains that seem to buzz or hiss during certain storms. Modern acoustical physicists suggest that this sound may be the result of synchronized grain motion and micro-discharge activity. A desert song hummed in voltage. But how exactly does dust create these effects? It begins with particle asymmetry. Smaller grains tend to lose electrons more easily than larger ones. As they bounce and slide in turbulent air, a separation of charge occurs. Smaller particles become positively charged and rise, while heavier, more negatively charged particles settle lower. This creates vertical electric fields within the swirling vortex. In large enough systems like haboobs, those rolling desert walls of dust that sweep across the Sahara or American Southwest, this charge separation can span kilometers. Field measurements taken in the Sahel region of Africa showed electric field strengths up to 10,000 volts per meter inside advancing dust fronts. That's enough to generate corona discharge along power lines, disrupt radio signals, and even produce faint visible light under the right conditions. It gets stranger still. In Australia's Simpson Desert, researchers found that some sandstorms produce so much static electricity that metal fences sparked during the event. This was verified by a team from the University of New South Wales, who used conductive rods to detect electrical discharges as the storm approached. Their instruments captured small arcs, actual sparks leaping between metal rods, triggered purely by charged dust particles. It's a reminder that the planet's driest places may be among its most electrically alive, and this behavior isn't limited to Earth. As I mentioned earlier, Mars is an active participant. Images from orbit show dust devils, etching long paths into its surface, and more than one rover has found its solar panels suddenly cleaned, likely brushed by passing devils. But with that cleanliness comes static. Studies from the Jet Propulsion Laboratory suggest that Martian dust storms could, under the right conditions, generate discharges strong enough to affect onboard circuits or instruments. Which raises an old question in new form. Could life, if it ever existed or still exists on Mars, have been influenced by electrostatic chemistry? On Earth, laboratory simulations have shown that electric discharges in dusty gas environments can spark complex organic reactions. Researchers at the University of Tokyo replicated desert lightning in sealed chambers and found traces of nitriles and simple hydrocarbons forming in the dust, a dusty twist on the famous Miller-Urey experiment. Static sparks may not just irritate our electronics, they might light the fuse for life itself. So next time you see a dust devil pirouetting across a dry field, consider the invisible drama inside. Electrons are shifting, fields are forming, tiny chaotic charges leap from one grain to another, humming with potential, and whether on Mars or Mongolia, each swirl of dust carries a whisper of lightning waiting to find its voice. If dust and deserts can whisper of lightning, then it's only natural that scientists would try to make the sky speak on command. For all the strangeness of electric lights in nature, there's something even stranger about trying to build them from scratch. So now let us step into the humming laboratories of the curious and the brave, those who, armed with coils, sparks, and containment chambers, have tried to recreate exotic lightning under human hands. Ball lightning, St. Elmo's fire, volcanic discharges, all are captivating in the wild. But they are also unpredictable, and researchers are nothing if not persistent tinkerers. Over the decades, dozens of labs around the world have tried to summon nature's rarer electrical phenomena indoors. The results, as you might imagine, range from controlled wonder to spectacular accidents. One of the earliest pioneers in this space was of course Nikola Tesla, in his Colorado Springs lab, at the turn of the 20th century. Tesla worked with what were then the largest man-made electrical discharges ever produced. His enormous coils generated arcs more than a dozen meters long, filling the room with crackling plasma. Tesla didn't just want to light bulbs wirelessly. He believed he could transmit electricity across continents using resonant frequencies. While his grand plan didn't quite pan out, his work laid the groundwork for the modern Tesla coil, a device still used today in classrooms, stage shows, and experimental physics labs. The Tesla coil creates high-voltage, low-current electricity, which produces visible arcs that dance through the air like electric vines. While it doesn't quite simulate ball lightning, it has allowed scientists to study arc behavior in controlled settings, how discharge patterns form, how they react to obstacles, and what frequencies influence their structure. In more recent decades, researchers have shifted their focus from brute force discharges to more targeted efforts. A fascinating development came in the early 2000s, when physicist Mike Dunning in New Mexico stumbled upon a way to produce glowing plasma spheres using microwave pulses. He wasn't attempting to simulate ball lightning at first. His goal was propulsion research. But during a series of tests involving microwave waveguides, he noticed something peculiar. Under certain conditions, glowing balls of plasma appeared inside the test chamber, hovering for several seconds before dissipating. Dunning and his colleagues refined the technique, eventually producing stable, floating spheres about the size of a small apple. These plasma balls bore a striking resemblance to eyewitness descriptions of natural ball lightning, glowing, self-contained, and strangely quiet. Further experiments showed that these orbs were composed of hot, ionized gas, surrounded by a cooler sheath of air, maintained by resonant microwave fields. They couldn't pass through walls or windows, but they could drift and hover briefly, fueled by the surrounding microwave energy. This work sparked global interest. In Japan, a team at the Tokyo Institute of Technology recreated similar plasma orbs in a microwave oven using graphite dust and controlled atmospheres. The trick they found was placing a thin layer of carbon on a glass slide, which, when exposed to intense microwaves, would ignite and produce a small contained plasma ball. These were short-lived and rather smoky, but again the resemblance was eerie. Naturally, some adventurous individuals took this concept to YouTube, producing homemade microwave plasma experiments using grapes, matches, and careful manipulation. Grapes, as it turns out, can create plasma arcs when microwaved in pairs due to the way their moisture content focuses energy between the two halves. This is less a path to controlled science than a ticket to replacing your microwave, but the underlying physics is genuine. High-frequency electromagnetic fields can concentrate energy and induce ionization in surprising ways. Elsewhere, the challenge has shifted towards simulating other exotic lightning types. At the University of Munich, Corrado Cimarelli's team constructed an artificial volcano, a high-pressure pipe blasting ash and gas into a sealed chamber. The goal, to recreate volcanic lightning under lab conditions. They succeeded within the chamber. Collisions between ash particles built up enough charge to trigger visible sparks. By adjusting the ash composition and particle sizes, they were able to study how different minerals influence the discharge patterns, offering insight into the chemical signature of natural eruptions. Then there's St. Elmo's fire. Recreating this in a lab is a matter of fine-tuning electric fields and geometry. Using pointed electrodes and a high-voltage power supply in a humid chamber, scientists have consistently generated corona discharges that match the glow and sound of St. Elmo's fire. A study at MIT even showed that small corona discharges around aircraft wings could be used to detect the onset of dangerous electric buildup, suggesting a modern application for an ancient sailor's omen. But perhaps the most ambitious attempt to understand exotic lightning involves computer simulations and laser-induced discharges. Using femtosecond lasers, pulses lasting quadrillionths of a second, researchers at the University of Geneva have managed to create lightning conduits in air. The laser ionizes the atmosphere in a narrow path, allowing a discharge to follow it. This method has even been tested outdoors during actual thunderstorms, with the aim of directing lightning safely toward a target, a sort of guided handshake between sky and ground. In one trial, the laser was aimed skyward during storm conditions at the top of Mount Sentis in Switzerland. The result, a controlled lightning strike that followed the laser-created path. It wasn't exotic lightning in the ball or sprite sense, but it was evidence that we might soon be able to coax lightning itself into playing by our rules. Still, the ultimate prize remains elusive. True ball lightning, the kind that slips through walls and lingers in mid-air, has never been conclusively replicated in full. Most lab-generated plasmas require containment or energy input. They don't self-sustain like their folkloric counterparts. And perhaps that's just as well. If ball lightning is a rare convergence of atmospheric conditions, soil chemistry, and pure chance, maybe it's not something we're meant to bottle, yet the pursuit continues. From microwave plasma chambers to volcano simulators, from balloon-borne sensors to laser lightning rods, the laboratory becomes a kind of enchanted workshop, not to tame nature, but to mirror it, to learn her secrets by building reflections. Because somewhere between the coil's hum and the spark's dance lies the question we keep asking: if nature can make such wonders by accident, what might we create on purpose? If the coils and chambers of our laboratories have limits, perhaps the answers lie farther out, at the edges of matter itself. Let's now drift into a territory more speculative, where physics stretches and the universe leaves tiny fingerprints in lightning's glow. Because for some researchers, the ordinary explanations aren't quite enough. They believe these exotic electrical events may hint at something stranger, not just unusual weather, but fundamental quirks of reality itself. Could ball lightning and other strange flashes be, in part, quantum tricks? Could the sky in its momentary brilliance be reacting not just to atmospheric shifts, but to deeper forces, subatomic, invisible, maybe even cosmic? Let's start with one of the boldest ideas: antimatter. Not the sci-fi kind used to power spaceships, but real, tangible antimatter, the mirror counterpart to ordinary matter. Every particle in our universe has a twin with opposite charge. A proton has an antiproton. An electron has a positron. When matter and antimatter meet, they annihilate each other in a release of pure energy. Most of the antimatter created naturally on Earth comes from high-energy cosmic rays. When these rays strike the upper atmosphere, they can generate showers of particles including positrons. Under normal conditions, they vanish quickly, colliding and disappearing. But in powerful electrical storms, something odd happens. Satellites like NASA's Fermi Gamma Ray Space Telescope have detected brief flashes of gamma rays from thunderclouds, known as terrestrial gamma ray flashes. These bursts sometimes include positrons, antimatter particles, streaming upward. In other words, thunderstorms may be natural particle accelerators, capable of producing antimatter in small doses. Researchers like Joseph Dwyer, a physicist at the University of New Hampshire, have studied this phenomenon for years. His models suggest that electric fields in storms can become strong enough to accelerate electrons to near-light speed. These electrons then emit gamma rays, which in turn spawn positron-electron pairs. It's not a stretch to ask, could some strange lightning events, especially those involving penetrating light, odd spectral patterns, or persistent glow, be tied to these antimatter interactions? Perhaps not entirely caused by them, but influenced. It's a hypothesis still under investigation, but one that offers an enticing possibility that a thundercloud might, for the briefest instant, become a gateway to the quantum realm. From antimatter, we glide into another theoretical fog, the quantum vacuum. To understand this, we have to abandon the idea that empty space is empty. According to quantum field theory, even the vacuum of space is a seething ocean of virtual particles, popping in and out of existence too quickly to be seen directly, yet affecting real processes like the Casimir effect or the Lamb shift in atomic behavior. Some physicists speculate that under extreme electric fields like those found near ball lightning or certain upper atmosphere discharges, the vacuum itself might behave strangely. Theories propose that these conditions could momentarily polarize the vacuum, allowing energy to condense into visible effects. This idea is extraordinarily hard to test, but if true, it would mean lightning might, under rare circumstances, interact with the very fabric of space-time. You might say it's a bit of a long shot. You'd be right. But then lightning has always enjoyed long shots. There's also the matter of dark matter. That elusive substance, detectable only by its gravitational effects, makes up roughly 85% of the universe's mass. We can't see it, touch it, or directly measure it, but we know it's there because galaxies don't spin the way they should unless something invisible is tugging at them. Some fringe researchers have suggested that certain rare electrical phenomena might occur when Earth passes through denser regions of dark matter, or when high-energy interactions briefly affect dark matter particles. It's a deeply speculative field, and no peer-reviewed study has confirmed such a link. Still, the idea that some unexplained lights could be flashes of interaction between visible and invisible matter persists in corners of the theoretical physics world. In more grounded speculation, plasma physicists have explored whether stable plasmoids, structures made of ionized gas, could exist longer than expected under certain field geometries. A plasmoid in this context is a donut-shaped or spherical collection of plasma that maintains its shape due to internal magnetic fields. These have been observed in fusion experiments, and intriguingly, in the wake of certain lightning strikes. Could ball lightning be an accidental natural plasmoid? Researchers at the Russian Academy of Sciences once created such plasmoids using intense microwave radiation in a gas-filled chamber. These blobs of glowing plasma lasted several seconds and floated briefly before dissipating, mimicking, at least superficially, the behavior of ball lightning. Yet again, the mechanism wasn't entirely clear. Some scientists posited that the interactions might involve not just plasma, but interactions with electromagnetic vacuum fluctuations, blurring the line between classical and quantum physics. And then there's string theory. This elegant but still unproven framework suggests that particles are not point-like but tiny vibrating strings of energy. In some interpretations, certain high-energy events, like the kind that occur in upper atmosphere lightning, might momentarily access higher dimensions or reveal hidden symmetries of space. These ideas are for now more poetic than practical, but they speak to a truth scientists often feel: the deeper we look into nature, the more it looks back with mysteries. What ties all this together isn't just speculation, it's the sense that exotic lightning sits at a crossroads, between atmosphere and vacuum, between classical physics and quantum mechanics, between the known and the possible. When you see a sudden orb of light drift through a room, or a flash split the sky with no storm around, perhaps it's not just weather, Perhaps it's a whisper from the underlying code of the universe, flickering briefly into view, and maybe, just maybe, these phenomena are telling us that we don't yet know where physics ends, or what it's capable of beginning. And just when you think these luminous wonders live only in clouds or plasma chambers, the ground beneath our feet reminds us it too is listening. Sometimes in the hours or days before a great upheaval, before the earth heaves and rearranges itself, strange things happen. Not in the sky, but in the circuits. In the flicker of a light bulb, in the static of a phone line, in the instruments we trust to be neutral observers, because sometimes the machines notice before we do. These are the electrical anomalies that precede major disasters. Flickers, surges and pulses that seem to whisper of danger, moments before the fault lines crack or the mounting groans. Let's begin with a flicker. Literally, in 2007, hours before a magnitude 8 earthquake struck the Solomon Islands, technicians at a coastal radio station recorded sudden, unexplainable power fluctuations. Their voltage stabilizers spiked and then flatlined for several minutes before returning to normal. Later analysis found no local equipment fault, no weather interference, just a glitch. Or consider the 1989 Loma Prieta earthquake in California. In the days leading up to the quake, sensors near the epicenter picked up inexplicable changes in magnetic field intensity, variations well beyond normal diurnal shifts. These anomalies were reported by multiple stations, including one near Corralitos, where an unusual signal lasting several hours was captured. It wasn't until after the quake struck that researchers took a closer look. These signals fall under a broader category known as seismic electromagnetic precursors. It's a clumsy term, but an important one. Scientists have long wondered whether earthquakes, like some restless animal, fidget electrically before they roar, and there's growing evidence that the answer might be yes. The phenomenon may begin deep underground. As tectonic stress builds in the Earth's crust, microfractures begin to form. In quartz-rich rocks, this mechanical strain can liberate electrical charges, a process related to the piezoelectric effect, but on a massive scale. Friedemann Freund, the same physicist we met in our earlier discussion of earthquake lights, has proposed that these stressed rocks generate mobile positive charges, which migrate to the surface and disrupt local electromagnetic environments. These migrating charges could influence everything from the ionosphere above to the power grids nearby. In some areas, such as central Italy, researchers have observed consistent drops in ground conductivity leading up to seismic events. In one case, days before the 2009 L'Aquila earthquake, instruments detected sharp changes in ground resistivity. At the same time, local residents reported unusual behavior in electrical appliances, clocks running fast, LED lights blinking without power, and battery-operated radios producing static. You might be thinking, surely these are coincidences. And indeed, many in the geophysical community remain cautiously skeptical, but there is enough pattern to warrant attention. Japan's HyNet seismic network has been collecting not only ground motion data, but electrical field measurements for years. Following the 2011 Tohoku earthquake and tsunami, researchers reviewed the records and found elevated levels of ultra-low frequency electromagnetic activity in the days before the quake. These ultra-low frequency waves are thought to originate from the ground and travel upward, influencing the ionosphere and perhaps even radio transmissions. Some satellite systems, like the French detection of electromagnetic emissions transmitted from earthquake regions, were designed specifically to monitor such signals. Demeter detected anomalies in electron density and electromagnetic emissions over known fault zones, occasionally just hours before large seismic events. While not every anomaly led to a quake, and not every quake was preceded by an anomaly, the overlap was intriguing. Then there's the curious case of animals behaving oddly before earthquakes, a phenomenon reported for centuries. Dogs barking, birds fleeing, cattle restless without reason. One emerging theory is that animals may be sensitive to subtle changes in the local electric field, essentially detecting the Earth's electrical unease before our instruments do. If animals can sense it, why not our electronics? Indeed, high-voltage power lines have in a few cases acted as accidental sensors. Before the 1995 Kobe earthquake, engineers noted odd fluctuations in line voltage, small but measurable deviations in current. Similar disturbances were observed in Taiwan before the Chi-Chi quake of 1999. And in Turkey, geophysicist Alper Senyorek led a project to monitor electrical noise levels along fault zones. His early results suggested consistent spikes in electrical interference in the hours leading up to significant tremors. Of course, drawing a straight line from a flickering light bulb to a tectonic event is tricky business. Human perception thrives on pattern, especially after the fact. Anecdotes abound. But distinguishing real signals from random noise remains a scientific and statistical challenge. Yet the idea persists that the Earth might emit warning pulses, however faint, before it ruptures, like the subtle muscle twitch before a sneeze, or the hum of a violin string just before it snaps. It's no surprise, then, that earthquake prediction projects increasingly include electromagnetic monitoring alongside seismic arrays. New initiatives in Chile, Nepal, and Indonesia deploy ground-based antennas and aerial drones to watch for telltale electrical changes. Some even propose that early warning systems could incorporate these signatures into their algorithms, if not to predict, then at least to supplement and understand. In a way, these anomalies are the Earth's secret footnotes, easily missed, easily doubted, but possibly vital. They're not loud, not like sirens or thunder. They arrive as whispers, shifts in current, tiny sparks in the dark, odd clicks on a radio dial. Not prophecy, but possibility. And if we learn to listen, truly listen, perhaps one day our instruments won't just tell us what happened, they'll tell us what's coming. If strange electrical whispers do echo through the Earth before disaster, the question becomes not just whether we can hear them, but whether we can make sense of what they're saying. So now we arrive at perhaps the most compelling question of all: could these luminous, charged and curious signals actually help us predict extreme events? Prediction, after all, is the scientific holy grail of disasters. We dream of giving people even a few extra seconds, just enough to step out of an elevator, shut down a reactor, move a child to safety. And the idea that nature might offer signs, even fleeting ones, has long fascinated researchers, especially when those signs shimmer with electricity. Let's begin with earthquakes. We've seen that electromagnetic anomalies sometimes precede seismic activity: spikes in ultra-low frequency waves, sudden voltage shifts, ionospheric glitches. The challenge is that these signals are not consistent. Some earthquakes arrive with electrical fanfare, others slide in silently, like a cat on carpet. So the real task becomes one of patterns, recognizing not just isolated sparks but meaningful sequences. In Greece, a group of researchers led by Panayorios Foros developed what they called the VAN method, named for their initials. They focused on seismic electric signals, short, low-frequency pulses that appear hours or days before earthquakes. Using a network of sensors across the country, they claimed to predict several medium to large quakes with surprising accuracy. Their work was met with both acclaim and sharp skepticism, especially since the predictions were sometimes vague in location or timing. Yet the method remains in use, quietly gathering data and refining itself. In Japan, where seismic preparedness is nearly a national identity, researchers at the Earthquake Prediction Center in Chiba have been investigating correlations between changes in local ground resistivity and seismic activity. In several documented cases, regions near impending fault ruptures showed sharp declines in electrical resistance days before the quake. This may be due to fluid movement underground, electrolytes pushed toward the surface as rock strata shift, changing the way current flows through the Earth. Meanwhile, satellites like China's China Seismo-Electromagnetic Satellite continue the work begun by earlier missions like Demeter. These orbiters monitor the ionosphere, scanning for signs of electromagnetic turbulence that might correspond with tectonic rumblings below. In some studies, a drop in electron density above quake zones has been observed just hours before impact. The cause remains elusive, perhaps outgassing of radon, perhaps charge migration through rock, or perhaps something yet unnamed. Beyond earthquakes, researchers are also exploring predictive signatures in volcanic activity. Before a volcano erupts, magma moves, often quietly at first, but with increasing turbulence as pressure builds. This movement can generate both seismic tremors and electrical signals. In Iceland, near Hekla volcano, scientists have installed sensors that monitor not just vibrations but local electric field strength. In one test case, a surge in electrostatic potential was recorded nearly 12 hours before a minor eruptive event, coinciding with increased degassing and ground deformation. A similar effort is underway in Italy, where Mount Etna's frequent burps offer a laboratory of sorts. Researchers at the National Institute of Geophysics and Volcanology have linked spikes in atmospheric electricity with episodes of strombolian activity, those rhythmic bursts of lava and gas that make Etna a favorite among volcanologists. They're even experimenting with drones that can sample electric field gradients above fumaroles, hoping to detect subtle changes in volcanic respiration. But perhaps the most surprising predictive arena is space weather. Solar flares and coronal mass ejections send showers of charged particles toward Earth, sometimes disrupting satellites, radio transmissions, and power grids. In rare cases, these geomagnetic storms seem to trigger lightning outbreaks, possibly by altering the upper atmosphere's electrical profile. Could monitoring the sun help us forecast lightning storms? At the University of Reading in the UK, researchers have studied correlations between solar activity and terrestrial lightning frequency. Their findings suggest that strong solar wind streams may, within days of arrival, boost lightning rates in certain storm systems. It's not a direct trigger, but a kind of energetic nudge. By ionizing the upper atmosphere, the sun may subtly lower the threshold for lightning to spark back on Earth. Artificial intelligence is being enlisted to parse the complexity. Machine learning algorithms, fed with years of electromagnetic, seismic, and atmospheric data, are being trained to spot predictive patterns humans might miss. The hope is that these systems can distinguish between the noise of everyday geophysical activity and the quiet signals of something building beneath the surface. One promising approach is multimodal fusion, combining data streams from electromagnetic sensors, gas detectors, seismic arrays, and even animal behavior monitoring. If a pattern repeats, a burst of ULF noise, a shift in ionospheric charge, a migration of toads from a riverbed, the system might flag a warning. Not a certainty, but a probability. Enough perhaps to act. Skeptics rightly note that such predictions must clear a high bar. False alarms erode public trust. Missed warnings cause heartbreak, yet proponents argue that even imperfect alerts could save lives, especially if they give seconds, not hours. Seconds matter. A train slowed, a control room alerted, a crowd gently redirected. There's also an ethical elegance to this work. It listens, it waits, it assumes the Earth is speaking in subtle voltages and vibrations, and asks only to understand, which brings us back to lightning. If certain exotic lightning events, ball lightning, earthquake lights, luminous glows, coincide with tectonic stress or magma movement, they may serve as visual signatures of underlying energy. They might not be random at all, just misunderstood messages. So could we one day predict disasters using light, not by gazing into the clouds like oracles, but by tuning into the charged hum of our planet? Perhaps the sky may not be prophetic, but it is reactive, and in the right conditions it may tell us what's coming, not with a shout but with a spark. To chase lightning is to look up, but if we look far enough past the storm clouds and weather fronts, we begin to see that the sky is not where the story ends, it's where it begins again. For above our atmosphere, beyond the shimmering sprites and faint auroras, lie the cosmic forces that help shape the storms we know. Solar flares, cosmic rays, and the invisible winds of space all touch our planet in ways subtle and spectacular. So now let us lift our gaze not to the clouds but beyond them into the electric theatre of the cosmos. The first cosmic character in this story is our familiar and somewhat moody star, the Sun. Every so often, the Sun releases a solar flare, a sudden powerful burst of radiation and charged particles that travels outward in all directions. Sometimes this comes with a coronal mass ejection, a great bubble of plasma and magnetic field hurled toward the solar system. When these solar tantrums hit Earth, they compress our magnetosphere, energize the ionosphere, and if strong enough, shake things up down here. Most people know solar storms for their visible effects, auroras rippling toward the equator, GPS glitches, or faint radio interference. But these events also change the electrical makeup of our upper atmosphere. By bombarding it with charged particles, they increase its conductivity. This can amplify existing electric fields and even shift the thresholds required for lightning initiation. In fact, studies from institutions like the University of Reading and Kyoto University have found that after major solar events, the global lightning rate can rise noticeably for several days. It's as if the sky, already full of tension, becomes just a bit more willing to discharge. The exact mechanism isn't fully known, but it likely involves enhanced ionization of the upper troposphere and lower stratosphere, where storm clouds flirt with cosmic influence. But it's not just our sun that plays a role. Enter the cosmic rays, high-energy particles from deep space, mostly protons, that zip across the galaxy at nearly light speed. When these particles slam into Earth's atmosphere, they collide with air molecules, triggering cascades of secondary particles. This constant bombardment creates what's known as air showers, showers not of rain, but of energetic particles and short-lived subatomic fragments. Here's where it gets truly fascinating. A growing body of research suggests that cosmic rays may help trigger lightning. The idea is that in strong electric fields within thunderclouds, a single energetic particle from space could provide the initial spark needed to start a runaway electron avalanche, a chain reaction that ultimately leads to a lightning bolt. This theory, known as the runaway breakdown model, was pioneered by scientists like Alex Gurevich in Russia and continues to be tested today. In one remarkable experiment, researchers in Japan synchronized cosmic ray detectors with lightning sensors, finding a statistically significant overlap between cosmic ray hits and lightning initiation. The implication: some bolts of lightning may begin with a cosmic nudge, an atom from a distant star, having wandered across space for eons, finally causing a spark in our sky. If confirmed, this would make lightning a kind of cosmic handshake, a meeting point between Earth and the universe. A reminder that we are not so isolated after all. There are also rarer phenomena, like the effects of geomagnetic storms on high-latitude lightning. During intense solar events, the Earth's magnetic field bends and snaps, creating massive currents in the upper atmosphere. These currents, known as auroral electrojets, can create voltage differentials large enough to affect ground-based systems, and may also influence lightning activity in polar regions. In fact, a series of studies from the Finnish Meteorological Institute found that during geomagnetic disturbances, the pattern of lightning activity across northern Europe shifted not just in intensity but in location. Storms that would typically flicker over the Baltic Sea shifted inland, following altered atmospheric conditions likely influenced by magnetospheric currents. Even stranger are the studies examining seasonal variations in lightning patterns that correlate with the Earth's passage through the galactic plane or through regions of increased cosmic ray flux. It's too early to say whether these long-term cycles have a measurable impact, but the suggestion lingers that our planet's electric life is shaped not only by weather but by our position in the grand spirals of the Milky Way. And then, there's the most delicate force of all, the background radiation of the universe, the ever-present, whispering trace of the Big Bang. While it does not directly affect lightning or storms, it is, in a poetic sense, the electrical silence from which all our sparks emerge. Every voltage, every discharge, every bolt through cloud or air or dust, each arises in a universe still echoing from its own creation. So where does this leave us? It means that exotic lightning is not only a local event, it is a dialogue, a call and response between Earth and space, between thunderclouds and solar winds, between drifting atoms and geomagnetic tides. And when the bolt flashes, it's not just weather, it's an expression of connection, a punctuation mark in a sentence that began far beyond our sky. It reminds us that the energy swirling in our storms has siblings in stars, that the flashes we watch from our windows are cousins of the radiation streaming from quasars and novae, that sometimes the spark that leaps from a cloud may be finishing a journey begun millions of light years ago. The next time lightning splits the sky, you might wonder, was that started by a proton from a supernova, a murmur from a magnetic storm, or a gentle push from the sun's restless breath? Whatever the answer, it's clear now, every storm listens to the stars. If the stars play a role in our storms, then it seems only fair to ask who else is listening. Because while we build our instruments and decode our satellite feeds, we are not the only ones tuned in to the electrical hush before the flash. Across plains, oceans, treetops and riverbeds, a quieter audience moves through the world, birds, beasts, fish, and all their kind, sensing something we cannot quite name. Some of them flee before the quake, some grow agitated as the pressure builds, and others seem simply to know, long before we do, that the sky is about to speak in sparks. Let's begin with the pigeons. Homing pigeons, those feathered navigators of myth and messenger, are famous for their uncanny ability to find their way home, sometimes across hundreds of miles. Research at the University of North Carolina has shown that pigeons may possess magnetoreceptors, cells, possibly containing magnetite, that allow them to sense changes in Earth's magnetic field, These same sensors might also detect subtle electric fields, or at least be affected by the same atmospheric changes that precede lightning, quakes, or eruptions. When the air crackles, when the charge builds, the birds feel it. In 1975, in the Chinese city of Haikeng, local reports of unusual animal behavior prompted officials to evacuate. Snakes emerged from frozen burrows in midwinter, chickens refused to roost, dogs howled, and perhaps most strangely, insects took flight in thick clouds. Days later, a major earthquake struck, devastating the region, but the human death toll was far lower than expected, in part because so many had left early. Coincidence? Perhaps. But in the years since, scientists have tried to quantify these behaviors. At the University of Duisburg-Essen in Germany, researchers outfitted cattle with GPS collars and motion sensors. They found that cows often align their bodies along geomagnetic lines, but that this alignment becomes erratic before seismic events. The implication is that shifts in the electric or magnetic field may trigger physiological responses. Animals may not predict disasters in a conscious way, but they may feel the approaching change like a tremor in the skin. Electroception, the ability to detect electric fields, is well documented in aquatic species. Sharks, rays, and certain fish possess specialized organs called ampullae of Lorenzini, which allow them to sense the faintest electrical signals in water. Some species of catfish and eels can detect changes in electric fields caused by other organisms, or, intriguingly, by distant weather events. In the Amazon, electric fish have been observed altering their communication signals just before storms arrive, possibly responding to barometric shifts or electric charge in the air. There's even evidence, albeit limited, that migratory birds adjust their flight paths based on electric field conditions in the atmosphere. Experiments conducted at the Max Planck Institute for Ornithology showed that zebra finches exposed to altered magnetic and electric environments changed their restlessness patterns. These changes, called Zugunruhe, German for migratory anxiety, appear to be tied not only to light and temperature, but to electromagnetic cues. Might some of these same sensitivities explain how animals react before earthquakes or electrical storms? Some herders have long claimed they can tell a storm is coming not from the sky, but from their livestock. Horses grow uneasy. Elephants raise their trunks and turn away from unseen threats. In Sri Lanka, following the devastating tsunami that came after a powerful undersea quake, local villagers recalled elephants stampeding to higher ground well before the waters rose. Birds had vanished from the trees. Dogs refused to leave shelter. While the seismic waves had not yet reached the coast, something, perhaps an infrasonic rumble, perhaps an electrical ripple, had tipped them off. Infrasound is one possibility. These are sound waves below the range of human hearing, generated by large-scale events like earthquakes or distant explosions. Many animals can detect them, but there's also a growing theory that some species may pick up on changes in atmospheric conductivity, shifts in the electric potential between the ground and the sky. In 2021, a research team in Taiwan outfitted goats and cows with biologgers near fault lines. In the days before a minor earthquake, the animals displayed marked changes in heart rate and movement, suggesting stress responses without an apparent environmental trigger. Correlating data showed a drop in ground resistivity and a mild spike in atmospheric ions, subtle electric cues, but enough to raise alarm in those whose senses are tuned differently. All of this suggests that Earth is a vast field of signals, some loud, some whisper soft, and among its inhabitants, some are built to listen in ways we are only beginning to understand. If we could tap into this bioelectrical awareness, if we could translate animal behavior into early warning, perhaps we'd add another layer to our disaster readiness, not replacing machines, but supplementing them with ancient senses. After all, what is science, if not the art of noticing what others overlook? Maybe the pigeons circling strangely know something about an ionospheric shift. Maybe the restless fish have heard a rumble in the voltage. Maybe the silent tree frogs, falling quiet before the storm, are telling us more than we think. And perhaps, somewhere in the whisper between the charge and the spark, animals are already speaking in electricity. We just haven't learned the language yet. And now we arrive at the question most often asked in a whisper, especially when thunderclouds roll in. What happens when lightning chooses you? For all our fascination with exotic bolts and ghostly fireballs, there's something deeply personal and frankly unsettling about the idea that electricity might seek out the human body. Let's take a slow and steady look at what it means to be a lightning rod, literally and figuratively, because across centuries and continents, humans have found themselves struck, singed, lifted, stunned, or strangely transformed by encounters with skyborne electricity. It begins, as always, with the air. When lightning forms, it does so in stages. A thundercloud builds electric potential until a stepped leader, a jagged path of ionized air, reaches downward toward the ground. Meanwhile, the Earth sends up streamers, upward surges of electricity from tall or conductive objects. When one of these upward streamers connects with the leader, the path is completed, and current flows in a massive visible flash. Now, what counts as tall or conductive? A flagpole, a tree, a golf club, a human being standing upright in an open field, or hiking along a ridge. We are, it turns out, surprisingly good at offering ourselves up to the sky. Our bodies are conductive, made largely of water and salt, and when the air's electric field grows strong enough, we can generate our own invisible corona, just like a fence post or ship's mast. This corona isn't visible under normal conditions, but under the right storm-charged sky, it can briefly glow. There have even been reports of St. Elmo's fire forming on hikers' trekking poles or climbing gear. Not exactly the travel companion you want. There are stories, many true, some exaggerated, of people struck by lightning in bizarre circumstances. A park ranger in the Appalachian Mountains, Roy Sullivan, was reportedly struck 7 times across his life. He survived them all, earning a place in the Guinness World Records and a collection of scars, both literal and psychological. His hair was often singed, his hat once caught fire, and each time the strike left behind not just wounds but a mystery. Why him? Science doesn't offer a personal explanation, but probability theory does suggest that people who spend lots of time outdoors in certain regions have increased chances. Statistically, you're more likely to be struck if you're above the tree line on a lake or out in open terrain. Metal objects, contrary to popular myth, don't attract lightning, but they do conduct it once it's near. So holding a fishing rod or umbrella in a storm is not an invitation exactly, but it does make you an excellent conductor once the party starts. So what happens when lightning passes through a human? The results range widely. Some strikes are indirect, passing through the ground or a nearby object before arcing into a person. Others are direct hits. The current can range up to hundreds of thousands of amperes, though the duration is incredibly brief, usually less than a second. Still, the effects are dramatic: burns, cardiac arrest, nerve damage, ruptured eardrums, and in some cases memory loss or changes in personality. Yet not all strikes are fatal. In fact, a majority of people struck by lightning survive, often with lingering neurological or psychological effects. Some describe heightened sensitivity to electrical fields, migraines, or phantom sensations in their limbs. A few survivors report a strange, persistent buzzing just before storms, as if their bodies remember the path electricity once took. And then there are the patterns. Lichtenberg figures, also called lightning flowers, are branching fern-like marks that sometimes appear on the skin of strike survivors. These are not burns in the traditional sense, but rather scars formed by the rupture of capillaries just under the skin, tracing the path of electricity through the body. They're temporary but hauntingly beautiful. Nature's tattoo in electricity. There's also the matter of strange behavior in metal objects. Coins in pockets can melt. Zippers can leave burns. There are even recorded instances of metal fillings in teeth exploding from the heat, a dental surprise no one requests. Clothing, too, behaves oddly. Shoes are frequently blown apart. The rubber soles superheated by the current. Fabric may be singed but left intact. One survivor, interviewed in a National Geographic feature, described his shirt catching fire while his backpack remained completely untouched. And yet the body sometimes withstands what seems unthinkable. A bolt hot enough to vaporize bark from a tree somehow leaves a human upright, shaky but alive. Theories vary. One idea suggests that skin effect, the tendency of high-frequency currents to travel along the outside of conductors, may cause lightning to skim the outer surface of the body. Another hypothesis is that the current takes the shortest path to ground, bypassing vital organs if the external route is faster. Still, the margin is slim, and no one walks away unchanged. There are rare but credible accounts of people developing electrosensitivity after a strike, reporting discomfort near electronics, trouble sleeping under power lines, or anxiety during thunderstorms. Some of this may be psychological. Some may be neurological. The human body is not designed to be part of a lightning circuit. When it is, things shift. In more ancient times, lightning-struck individuals were seen as touched by the divine, either chosen or cursed. In some cultures they were revered as oracles or feared as harbingers. The Greeks believed that Zeus marked those he struck. Among the Yoruba of West Africa, those who survived lightning were said to be under the protection of Shango, the thunder god. Such people were often given roles in ritual, seen as go-betweens for earth and sky. Perhaps there is something in us that still senses the sacred or the uncanny when a person survives the sky's full attention. But lightning isn't personal, it's indifferent. It moves where the path is easiest, where the field is strongest, where the resistance is lowest. And sometimes that path happens to be through a person. It doesn't choose, it flows. And in the aftermath, what remains is not just scorched ground or shattered trees, but stories, scars that glow in retelling, bodies that remember, and a quiet, unsettling awareness that we are not separate from the elements, but part of their circuitry. Sometimes we're not just standing on the earth, we're connected, head to sky, breath to storm, spark to memory. Before we ever had words like electrons or a noosphere, before instruments and equations and sensors on weather balloons, we still saw the lights, and we gave them names. We called them sky serpents, dragon fire, spirit flames, and fox lightning. We feared them, we worshipped them, and when we could, we wove them into story. Let us pause now and look back, not through telescopes or field monitors, but through the long shimmering lens of myth. Because strange electrical phenomena may be among the oldest things ever witnessed, and for most of human history, the only way to record them was in song, in story, in carved stone or painted cave. Consider the will-o'-the-wisp, those faint flickering lights reported over marshes and bogs. In Europe they were said to be mischievous spirits, leading travellers astray. In Ireland they were known as jack-o'-lanterns, and in Scandinavian tales as swamp folk holding lanterns. These glows may well have been small natural plasmas, created by the oxidation of gases like phosphine or methane in moist organic-rich environments. Not exactly ball lightning, but kissing cousins, born of decay and electricity. Then there are the fireballs of East Asian legend. In Japan, tales of Hino-Tama, or fire spirits, describe glowing orbs drifting through forests or hovering over graveyards. The 1795 book Wakan Sansai Zu includes sketches of luminous balls witnessed by farmers after earthquakes, anecdotes eerily reminiscent of modern reports of earthquake lights. And across the Himalayas, travelers speak of the Dzinier, or lightning dragons, whose appearances were said to foretell avalanches or ground tremors. To this day, elders in Bhutan and Nepal recount sightings of glowing serpents writhing across the sky before seismic events, a folkloric parallel to the red sprites and blue jets we now know race upward from thunderheads. In the Andes, Incan priests spoke of sky stones that shimmered with light and vanished without sound. Some historians believe these could be early accounts of ball lightning, or at the very least of unexplained atmospheric glows during stormy seasons. What's remarkable is the consistency. Thousands of miles apart, cultures with no contact and no shared language describe similar lights, luminous spheres, tendrils in the sky, halos on mountaintops. And while the language differs, some see gods, others see demons, others see ancestors, the shape of the phenomenon remains. Take the ancient Greeks. They spoke of phors eknophilas, light from the clouds, which could be wrathful or guiding. Aristotle wrote of rolling thunder that could produce fire without sound, a curious note that may hint at ball lightning or corona discharge phenomena misunderstood in his time. Or turn to Norse mythology, where Thor's hammer strikes the earth not just with noise but with fire. Some sagas describe his descent to battle with trails of blue light behind him. Modern interpretations often gloss this as symbolic, but there's an electrical echo there, familiar now to those who study the streaks of St. Elmo's fire across ships and towers. In North America, indigenous tribes across the plains and mountains recorded stories of lightning beings, spirits that traveled inside storms or appeared as glowing orbs after tremors. The Ojibwe spoke of thunderbirds whose wings created the storm and whose eyes flashed with light. The Zuni spoke of Ashiwi, ancestral spirits who moved in arcs of electricity, guiding and warning. And in the deserts of Australia, Aboriginal rock art depicts figures with halos and tendrils, sometimes accompanied by zigzag lines interpreted by elders as sky paths or fire trails. Ethnographers now speculate that these drawings may represent ancient accounts of sprites or other upper atmosphere lightning. Even in sacred architecture, we find signs, atop the spires of Gothic cathedrals, long before the invention of lightning rods. Architects placed metal finials, ostensibly decorative, but often described in their own time as attractors of divine breath. Pilgrims spoke of blue glows around the towers during storms, and some even believed that lightning striking the spire purified the structure. What were these, if not early nods to electric truth? In modern times, the lines between folklore and science continue to blur. A 19th-century French farmer described a glowing orb that floated through his barn, causing no fire but singeing the wool on a sheep's back. He called it La Lumière du Diable, the devil's light, but when the tale reached the Paris Academy of Sciences, a physicist named Arago wondered aloud if it was a rare form of atmospheric electricity. Arago's notebook from that year includes sketches that look remarkably like ball lightning reports from the Soviet Aviation Corps over a century later. So here we are, with physics in one hand and myth in the other, still chasing the same flickering orb. Maybe that's the point. Perhaps these phenomena were never just scientific or spiritual. Perhaps they've always existed at the edge of both, inviting curiosity, stirring awe, reminding us that nature doesn't draw lines where we do. A glowing light in a storm may be ball lightning, or a fire spirit, or the touch of a god. The name doesn't change the glow, it only shapes how we carry it. In that way, science and myth are not rivals, they're traveling companions. Each offers a lamp, and sometimes when the path is strange and the air is charged, we need both lights to see. And so we arrive at the quiet edge of our journey, where questions deepen and certainty thins, where the sky's brief flashes meet the deeper silence of what we still do not know. Because after all the sparks and plasma, the sprites and stories, one truth hums beneath it all: our planet's electricity doesn't always behave the way it should. It flickers in unexpected places, it glows without fire, it leaps upward instead of down, and sometimes, just sometimes, it does things that science cannot quite explain, not yet. Let us close then, not with answers, but with listening. Because within these unexplained flashes and glowing orbs, there may be clues, not just about weather or geology, but about Earth's subtle workings, its prelude to catastrophe, and its quiet attempts to warn. Take, for example, the reports from multiple earthquake zones, where both natural sensors, animals and artificial ones, ground antennas, register changes long before seismic waves arrive. In Japan, before the 2011 Tohoku earthquake, ionospheric disturbances were detected 3 days in advance by both ground-based sensors and the French satellite Demeter. At the same time, residents reported malfunctioning electronics and sudden surges in voltage. Were these coincidences, or fragments of a warning system that we have not yet learned to read? Some researchers believe there is indeed a pre-seismic window, a brief but critical period in which the Earth's physical and electromagnetic properties begin to shift. During this time, rocks may fracture microscopically, releasing radon gas or producing piezoelectric effects that alter local electric fields. Atmospheric ions may increase, changing the conductivity of air and influencing cloud behavior. Radio waves may bend strangely. Even the color of the sky might subtly shift as light refracts differently through ionized air. None of these changes alone can predict a disaster, but taken together they offer a pattern like static before a song. And what about lightning? Could some forms, especially the rarest, serve as last-minute markers of instability? Ball lightning, often reported in the moments before or during seismic events, may be more than a curiosity. Some geophysicists propose that the electrical anomalies preceding an earthquake could create the conditions for ball lightning to form near the surface, via the sudden ionization of air, bursts of underground charge, or plasma release from stressed rock. These orbs might not just be a side effect, they might be a visual signature of stress, a firefly of tectonic tension. Similarly, earthquake lights, once dismissed as fiction, are now accepted as real but not yet fully understood. The exact mechanism, be it charge migration, radon ionization or atmospheric resonance, remains debated, but their timing is consistent. They appear in the minutes or hours before some major earthquakes, particularly in regions with high quartz content in the crust. These glows are not only real, they may be useful. If we can learn to detect and interpret such signals in the sky, on the ground, in the air, we may gain not just insight, but time. This idea is not without precedent. Meteorologists once relied entirely on pressure readings and cloud patterns to predict weather. Now, with satellites and Doppler radar, they can track storms in real time. Could the same tools refined for lightning, tuned for plasma, help us track the invisible precursors of tectonic unrest? Already, projects like Japan's earthquake early warning system and China's seismic satellite initiatives are beginning to include electromagnetic monitoring in their models. Meanwhile, in Europe, a cross-disciplinary project known as PR-Earthquake is investigating the full spectrum of pre-seismic phenomena, from ground gas emissions to ionospheric anomalies to low-frequency electric pulses. The hope is modest but profound, not to predict every quake or eruption, but to develop a layered alert system where even a strange glow in the sky might earn a second look. Because when the Earth prepares to move, it doesn't do so in silence. It rustles, it pulses, it glows. And perhaps the rarest electrical events, sprites, jets, St. Elmo's fire, even ball lightning, are not just curiosities of storm and sky, but part of a broader, older vocabulary, a language of signals, one that we're only just beginning to translate. Even today, new mysteries emerge. Satellite data shows unexplained high-energy bursts in clear skies. Remote cameras capture silent flashes above empty deserts. Field researchers log spectral emissions that resist classification. Sometimes the data doesn't match the models, and sometimes the models don't match the sky. But here's the quiet beauty of science. It leaves room for wonder. It allows us to say, we don't know yet. And in that yet lies all the curiosity that fuels discovery. So we end not with a conclusion, but with an open circuit. A loop waiting to close. Because somewhere another storm is building. Another mountain is shifting. Another spark is preparing to leap. And whether that spark is a warning or a wonder, whether it lights a forest or flickers over a ship's mast, it is part of the Earth's electric story. And so are we. Thank you, dear listener, for wandering through this glowing, crackling world with me. If you enjoyed this little journey into the secret life of lightning without storms, please consider leaving a like, subscribing, or leaving a comment. Sleep well, fellow traveler.